Kiddos, this video I'm going to introduce you to a notion called implicit differentiation. And to do so, we have to kind of think about what a function is. And so let's look at what really an explicit function is, and then we can think about an implicitly defined relation. So an explicitly defined function, right, basically kind of looks like this, right? We have y or even f of x is equal to some function of x, right? It's clear that this guy, y, depends upon those variables, independent variables, x, right? And so, for example, we have y equals, 3x squared plus 1, or y equals sine of x over x. And, we can get as messy as you would like to get over here. These here are, of course, functions. Y is a function of x. Y is a function of both of those x's, right, of x. X is the independent variable. Y is the dependent variable. Okay. Now, so far what we've done is we found that the derivative of y, dy dx, is f prime, right? And so, for example, this is nothing new here. If we take the derivative of 3x minus 1, so if y equals 3x minus 1, then y prime equals 3, right? Kind of running out of room there. If y equals sine x over x, then y prime, or dy dx, is equal to, by the quotient rule, low x d high minus high d low all over low. Okay. And of course, we have many rules to consider and ways in which we go about this. But either way, it's very clean the way we think of a function y in terms of x and differentiate y in terms of x, an explicitly stated function. Okay. However, what if we have, let's say, other kinds of relations, like circles, for example? And so let's talk about what an implicit relation or implicitly defined relation looks like and is. Okay, and I say relation because they're oftentimes not functions. In fact, the ones we look at will not be functions. So, and I like to think of these guys as kind of, you have x's and y's hanging out together, right? So it's not clear that y on one side is a function of x or many x's on the other side of that equal sign, right? And oftentimes these guys are not even functions. So let's look at some particular examples. And the most basic example of an implicitly defined relation would be a circle, right? And so if you recall, x squared plus y squared is 25. That's a circle. It has a center of 0, the origin. And the radius is going to be the square root of 25, which is 5, right? But regardless, you got x's and y's on the same side of the equation. It doesn't look like y equals some function of x, right? In fact, when you solve for y, which you could in this case, you could get y equals plus or minus 25 minus x squared. It's not a function anyway, right? And so another example of an implicitly defined relation might be sine of x plus y equals 3x plus x over y, right? You got a lot of x's and y's hanging out together, right? And it's not clear that y is a function of x. It's implicitly defined. Okay, in this case, probably not a function either. Okay, so that's kind of what those implicit relations look like, right? Here's kind of an easy, there's kind of a messy. Okay, so you might be saying to yourself, well, how do we find the derivatives for those guys? Well, the process is similar. So this is what implicit differentiation is. And first we have to recognize that it's appropriate to use this technique, which technically we're doing anyway, I suppose, when we have an explicitly defined function. And that's not how you spell differentiation. I'm missing the syllables. Okay. Number one, we want to differentiate both sides of the equation. Both sides, right? The left and the right side of the equation with respect to WRT x, right? And of course we have all these rules. We have the chain rule, we have the product rule, we have the quotient rule, Don't forget those rules, right? Okay, and there's an extra little rule that's going to pop up here, which I'll kind of leave for a second. And then basically after we've differentiated both sides, we want to isolate or solve algebraically for dy dx. That step is kind of algebraic. Okay? So let's look at this let's see what it looks like in practice, right? So here's the UC Davis math site, and there are a lot of good problems on here, so for those of you searching for more problems, there are lots here, right? If you scroll down, you have many problems, and there are some solutions that you can check out too if you like more. Okay, here's a website up here, or just search UC Davis, or just search implicit differentiation in your web browser. Okay, But this is a good problem to do. Thanks, UC Davis, for posting this. And it's pretty basic. So we have a function x squared plus y squared equals 25. Right? And what I want to do is I want to find, let's say, the slope of that tangent line there at 3. Right? What's the slope of this guy? And of course, to find the slope, I got to find the derivative. So it comes down to finding the derivative. How on earth do I find that derivative of that implicitly defined, in this case, relation? Okay, so let's go ahead and do that, see what happens. And so Miss Veltri showed me this wicked cool snippet tool, and we're going to use it right now. So I'm just going to snip this piece here and blow it up. Okay, so that's the function, the relation that I'm going to try to differentiate so that I can find the slope of that blue tangent line at 3, -4. Okay. So the first thing I want to do is differentiate both sides with respect to x. So I'm going to take the derivative of the left side, which is x squared plus y squared, and then I'm going to take the derivative with respect to x of the right, which is 25. Okay. Now, here's a little tricky piece here. When I differentiate x squared with respect to x, we get, as we would expect, 2x. Okay. However, when you differentiate y squared with respect to x, that y term is like an inner function because I'm differentiating with respect to x, and that y ain't an x. So therefore, when I differentiate that y squared with respect to x, the derivative of y squared with respect to x is 2y times, now by the chain rule, the derivative of y with respect to x, dy dx. Okay? So I suppose if we're kind of creating a recipe for doing these types of problems, bam, the red star here is when you have to tack on, use a chain rule, and by that I mean times dy dx whenever you have a y term, right? Whether it's y squared in this example, and you'll see some other examples shortly. Okay, so when you differentiate this y squared term with respect to x, its derivative is by the power rule 2y, and then by the chain rule times dy dx. Okay, and the rest is pretty straightforward. You differentiate a constant, 25, you get 0. That's step 1. Differentiate both sides with respect to x. Step 2. I'm going to solve for dy dx. So I'm going to subtract 2x from both sides. All right, gets rid of it there. And then I'm going to divide by 2y. And so I've solved, nope, I take one step further, negative x over y. Okay, so there's our derivative of this implicitly defined relation. And I found it by differentiating both sides with respect to x and solving for dy dx. Okay? Don't forget this little step here, times dy dx, when you differentiate y squared. Okay? And so now to answer the question, if I want to find the slope of the tangent line at 3, -4, I plug a 3 in for x. So the 3 goes in for x, and the -4 goes in for y, and I get 3/4. Okay? So that, therefore, would be the slope of that blue tangent line. Okay? I'm going to look at one more problem here, because why not? We're having fun. Let's look at a more difficult problem. This problem is called, or this particular relation is called a folium of Descartes. In Millersville website kind of provided this graph and this great page. I'm going to snip it, and we're going to think about it. Okay, I'm going to close this out, get a new one, and so let's see if we can grab that. Bam. Okay. Having fun with this new snippet tool, thanks to Miss Veltri. So here we have, in this case, an implicitly defined relation. So it looks like x cubed plus y cubed equals 3xy. Note that x's and y's are together. It's not y equals some function of x. So, and of course, the graph here is not even a function. It fails the vertical line test, blah, 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 blah. Okay? So my question for this one is, what's the derivative? What's dy dx? Right? What's the function that describes, well, not a function, but like a relation that describes the instantaneous rate of change of this folium of Descartes at any moment? So I'm going to use implicit differentiation. Why? Because that ain't a function. It's not y equals some function of x. To do so, I'm going to take the derivative of both sides with respect to x. So there's the derivative of the left, and I'm going to take the derivative of the right. Okay? Next up, I got to find the derivative. So I differentiate x cubed. That's nice and easy because it's with respect to x. When I differentiate y cubed with respect to x, it's going to be 3y squared times dy dx. Y times dy dx? by the chain rule, correct. Okay, y is like our inner function there. Okay, to differentiate the right side, what rule do we have to use? Well, the 3 is a coefficient, and then I have x times y. There's a rule that helps me find the derivative of x times y, or 3x times y, and that rule is the product rule, so I have to use a product rule. So if I'm thinking of it as 3x times y, it's going to be the derivative of 3x, which with respect to x, which is 3, times y, plus 3x times the derivative of y. Now the derivative of y, that particular factor, by the chain rule is dy dx. Okay. Now, once I've differentiated, I have to solve algebraically for that guy, right? There's one on each side. To isolate, I want to get them both on the same side. So I'm going to keep this guy on the right. I'm going to subtract the 3x dy from both sides. And I'm going to subtract the 3x squared. Oh my gosh, that's getting messy. Equals 3y, that stays, minus 3x squared. So all I did was I basically took this term right here, I subtracted it, and I took this term right here, subtracted it. Right? The reason I did that is because now my dy dx's terms are on the same side. I can factor it out. Okay, so I'm going to get on the right, I'm going to get dy dx times a quantity 3y squared minus 3x. And then on the right side, it's just 3y minus 3x squared. Okay, just algebra. Just got my algebra hat. So now to answer the question to solve for dy dx, now that I have dy dx isolated here, I'm going to divide both sides by 3y squared minus 3x. Right, so I end up with, on top, a lot of 3's here. Right, that's this piece, divided by the 3y squared minus 3x, the bottom piece. Okay, and that's a little messier problem, a little more difficult algebra, but certainly doable. That is implicit differentiation. Okay, here's the process. Don't forget the chain rule when you have a y-containing term, right? And sometimes this algebra here is a little messy, but certainly doable. All right, have a good day. We'll start with these questions tomorrow.